Hello and welcome. In the last session, we had an overview on slope failure modes and the methods to analyze them. The methods we commonly used for slope analysis are analytical, projection, numerical, and empirical. This session is on analytical methods for slope analysis. Analytical methods is to frame the problem in a well-understood form and equations, calculating the exact solution. In mechanics, many problems have well-defined solutions that are obvious once the problem has been defined and the framework is established, typically in the form of force and energy equilibrium. Then, a set of logical steps that we can follow to calculate the exact outcome. For slope analysis, the analytical equations are force equilibrium based. By calculating the forces pushing the slope down and the forces resisting the slope sliding. Since the analytical method involves defining and framing the problems in a well-understood forms and equations, it must have provided clear understanding of the problem. With analytical solutions, we have the advantage of knowing the specific reasons and the parameters leading to slope failure. Analytical solutions are generally rather long and complex, particularly if involving a number of parameters. Therefore, usually, analytical methods is limited to simple cases. It also requires many assumptions to simplify the solutions and the calculations. Let us first work on analytical methods for circular failure of rock slopes. This type of failure is general failure of slopes for soils and poor and weak rocks. For circular failure, the slope fails along a circular failure plane across the slope, as shown by illustration on the right. When circular failure occurs, the failure is sliding on a circular failure surface that has the least resistance through the slope. Therefore, it is possible to formulating equations in terms of sliding force and the sliding resisting force that are governing sliding along the failure plane. This is what soil mechanics adopted for slope stability analysis, using the limit equilibrium methods. The slope is usually simplified into two-dimensional. To formulate the equation, the techniques of method of slice are commonly used. If you have learned soil mechanics before, you would have learned slope stability analysis using the Bishop slides or the jumbo slides and perhaps a few more slides methods. I will not go through the method of slides in detail here. For those who want to learn the analytical methods, please read soil mechanics books. As we mentioned earlier, analytical method requires a number of assumptions when formulating the equations. The assumptions used for circular failure equations are: 1. Rock mass is homogeneous. The discontinuities such as joints are not considered. This assumption is valid for completely weathered, crushed, very highly fractured, and very weak rocks. 2. Rock mass shear strength is characterized by cohesion and friction angle. 3. Failure occurs in uncircular slide plane. 4. A vertical tension crack occurs in the upper surface or in the face of the slope. This is similar to the tension cracks in soils. The rock mass can be fully saturated or to be dry rock mass. Limit equilibrium method using method of slice technique is an iterative method. It starts with choosing failure planes and cut the sliding slope into slices. Then we will formulate an equilibrium equation of forces acting on each slide and the sliding driving force and the sliding resisting force along the sliding plane. For each slide, we can then compute the factor of safety as the ratio of resisting force to driving force. After doing the calculation for all the slices, we use the lowest factor of safety from all the slices of the slope. If the factor of safety is less than 1, the slope is no longer stable and will fail. In slope engineering, we usually require a factor of safety about 2 to 3. For toppling, the failure is by the rock block tipping over its corner. Usually, the rock blocks are already formed by subvertical joint sets. Those blocks can slide and rotate when forces are acting on them. Toppling is therefore governed by the geometry of the block shape and the resultant force. Tipping over can be easily analyzed geometrically, as shown by the illustration below. When the force W is inside the width B, the block will not tip over. Only when W line is outside the width B, the block will tip over around the base corner. The critical condition of tipping is expressed mathematically by the equation here. B over H equal to tangent of the tilting angle of the block. I have shown the diagram on the right in the last session. Depending on the geometrical configuration, we can have 4 possible scenarios governed by the block geometry, the tilting angle, and the base frictional angle. Toppling can occur only when B over H is smaller than the tangent of the block tilting angle, indicated by the 2 lower cases on the right diagram. Here is a summary of the geometrical and the mechanical conditions of toppling failure of rock slope formed by rock blocks. The summary is also shown on the diagram of the last slide. Rock block is stable when the tilt angle is smaller than the base friction angle, and B over H is greater than the tangent of the tilt angle. In this case, no sliding and no toppling. Rock block can slide when the tilting angle is greater than the base friction angle. But since B over H is greater than the tangent tilt angle, the block does not tipping over. This is the sliding only case. Toppling only is when B over H is smaller than tangent of tilting angle, but the tilting angle is smaller than the base friction angle. In this case, no slide, only toppling. However, when B over H is smaller than the tangent tilting angle and the tilting angle is greater than the base friction angle, we have sliding and toppling at the same time. Analysis of toppling failure can also use limit equilibrium analysis. Again, it is done by calculating the forces acting on the blocks and examining the equilibrium of the forces driving and preventing toppling of the rock blocks. A typical force diagram on a block subject to toppling is shown on the right. Toppling will occur when the resultant lateral force preventing toppling is less than the resultant lateral force driving toppling about the rotating corner. Sliding are checked by sliding driving force and the sliding resisting force, including the shear resistance at the base. Next, let us move to analytical methods for plane failure. We have learned the geometrical conditions for plane failure are: first, the sliding plane is parallel or near parallel to the slope plane. Second, the sliding plane daylights in the slope plane, which means the dip angle of the sliding plane is smaller than the dip angle of the slope. And third, the dip angle of the sliding plane is greater than the friction angle of the sliding plane. For analytical method to be used on plane failure, there are further assumptions. Usually, we simplify plane failure into 2D problems. First, to analyze the forces in the direction of sliding. With a 2D simplification, lateral resistance to slide on the two ends of the sliding block is ignored by considered negligible. Usually, we consider friction force only, and the cohesion of the sliding plane is not considered. Often, we need to assume the rock mass is either saturated or dry to compute the water pressure acting on slope. As illustrated by the diagram on the right, analytical equations for plane failure analysis is formulated by the equilibrium of all the forces acting on the sliding block, including body weight, water pressure, and the shear resistance. Factor of safety is calculated by resolving all forces acting on the slope into resultant for sliding resistant force and the sliding driving force along the sliding plane. The slope is stable if the factor of safety is greater than 1. Here is an example of analytical equations and a solution for plane failure in wet condition. The rock mass is assumed to be impermeable. The tension crack is filled with water. On the right, you can see a series of analytical equations to calculate the sliding driving force and the sliding resisting force along the sliding direction. Factor of safety is calculated as a ratio of the resisting force to the driving force. When the rock mass is dry, there is no longer any water pressure involved, and hence the equations for the solutions for plane failure in dry condition is much simpler than that in the wet condition on the last slide. Again, we need to formulate analytical solutions to calculate the sliding driving force and the sliding resisting force in the plane sliding direction. And from there, calculate the factor of safety. Again, a factor of safety less than 1 is an unstable slope. For log slope stability concerning wedge failure, analysis can be carried out using analytical method similar to the plane failure, but with more complicated force equations. Simply because of wedge failure, the sliding is on two planes that are forming the wedge. It can no longer easily simplify into 2D force diagram and the force equation. Force equilibrium is much more complex as it involves two planes. In fact, limit equilibrium analysis is only carried out when a specific single wedge is identified for stability analysis. I will not go through the analytical solutions for wedge slope failure. I have listed a book where you can learn the analysis if you wish to. I will just give you a couple of examples on the analytical equations for wedge slope analysis. Here is the simplest case, with the simplest solution for wedge failure sliding on two planes of same surface frictional angle. To further simplify the analysis, sliding is resisted only by friction. No cohesion is considered. The force diagram is illustrated on the left, and the force equations are on the right. Because there are two sliding planes involved, we have to introduce the wedge factor K, which is governed by the relationship between the inclination angle of the two sliding planes. K can be computed or found from the wedge factor chart. The chart is available in the slopes engineering book by Wiley. The equations presented on the last slide have assumed that the friction angles are the same for both sliding planes. However, in many cases, the two planes have different friction angles. Therefore, in formulating the analytical equations, different friction angle should be used for each sliding plane. The factor of safety for wedge failure sliding on two planes with different friction angle without considering cohesion is given here. The dimensional less factor A and B are found to be depending on the dip angle and the dip directions of the two planes. A and B may be found in a series of charts. Those charts are available in the rock slope engineering book by Wiley. Okay, we have gone through analytical solutions for general or circular failure, for toppling, for plane and the wedge sliding. We have learned that we can use limit equilibrium methods with method of slides developed in soil mechanics for circular failure of rock masses that behaves like soils, such as completely weathered, crushed, very highly fractured, and very weak rocks. Toppling failure happens with block mass with subvertical joint sets. The blocks are generally detached and can topple. Toppling can be analyzed by geometrical analysis, simply by checking block geometry and the tilting angle. Analytic methods can be used for plane and wedge failure. However, the solutions can be rather complex. Assumptions often oversimplify the problem, and the important factors cannot be analyzed. Analytical methods should be used only for single individual plane or wedge of large scale. I'm ending this session by giving you a couple of key references or reading materials. The book by Dr. Edward Hook and Dr. John Bray, titled Log Slope Engineering, is the original classical book on log slope analysis and design. This book was updated and revised by Duncan Wiley as the 5th edition in 2017. You can read the chapters on slope analysis to learn more on various methods of log slope analysis. Next session, we will continue with slope analysis using projection method. Goodbye and see you at the next session.